All right, everyone. This will be part one of the video for section 3.6, which is about derivatives of inverse functions. Specifically, we talk a lot about inverse trig, but that'll be for part two. In this part, we're going to start off by reviewing a little bit of algebra regarding inverses. So let's say that I want to graph the function over here, y equals x squared minus 4, with a domain restriction that x is greater than or equal to 0. To start off, I'm going to look at when x is equal to 0. So if I substitute 0 for x, I get negative 4, which puts me down here. And I can make my shape for the parabola using a few more points. So if I go over to x equals 1, y would be equal to negative 3. If I go to x equals 2, y would be equal to 0. And so on and so forth. So we know that this is going to make the right side of a parabola. Now, if I wanted to graph the inverse of y, I would need to take the points off of the graph of y and switch the x's and y's. So starting off with, let's identify these coordinates. For the one on the bottom, that is 0, negative 4. So on the inverse, we're going to plot the point for negative 4, 0. 1, 2, 3, 4. Then we have the coordinate 1, negative 3. So we'll plot negative 3, 1. Then we have the point 0, 2. Or not 0, 2, 2, 0. I misspoke. So we'll plot the point 0, 2. And rather than making the right side of a parabola, it is the top of a sideways parabola, which you might recognize as some kind of square root function, which makes sense because how do you undo square? You do that by square rooting. So we can actually find an expression for y inverse algebraically using kind of a similar idea, switching the x's and y's. So if the original function was y equals x squared minus 4, I'll be able to algebraically find an expression for y inverse by switching the x's and y's. X equals y squared minus 4. Now, since I'm undoing everything to get back to the inverse, I'm going to write y inverse here. And then we're going to solve for y inverse. So this brings up an important point. A lot of people, when they see this notation, assume that that negative 1 is an exponent. It's not. So this is not 1 over y. Not. All right, and when we get to inverse trig, that becomes even more common. So side note, what I just wrote here, that is called a reciprocal. That is not an inverse. Inverse is specifically when you undo all of the things that were done to x. All right, so think of inverse as opposite and reciprocal as flip a fraction. Yeah, they're different. So, solving algebraically, we would end up getting, we'd start by, we would start by adding 4 to both sides. And square rooting both sides. So we get y inverse is equal to plus or minus the square root of x plus 4. But here's the thing, that plus or minus would indicate that we have both the top and bottom part of the parabola. Here we only have the top part, so we're not going to worry about that negative root. Instead, we're just going to say the y inverse function is the positive root of x plus 4. And that actually came about because of this domain restriction that we put on the original function. And there was a reason we did that, because if I didn't put that restriction, the original function would have been a full parabola, which would mean that the inverse would have been a full sideways parabola. And the problem with that is that the full sideways parabola is not a function. It's a relation. It relates x and y, but it's not a function because it fails the vertical line test. That's to say, if I were to draw a vertical line anywhere on this function, well, relation, that vertical line would cross more than once. So because of that, we know that we would need this domain restriction to ensure that the inverse actually is a function. So if I were to take off this half parabola and go back to that original one that we worked with, the restriction allows the original to be what we call 1-to-1. Which means that for every x value, there's only one y value. Or actually, other way around. For every y value, there's only one x value that corresponds to it. With the original parabola, that definition fell apart because, for example, when y was 0, x could have been positive or negative 2. But by introducing that domain restriction, we make it so that there's only one y value for every x. Well, x value for every y, So now that we've kind of gotten a little bit of a algebra review, what happened? Let's talk a little bit about these derivatives. So if I were to find the derivative of the original function when x is equal to, say, 1. Remember, geometrically, what that tells me is the slope of the graph at that point. Meaning if I were to draw a tangent line at that point, it would tell me the slope of that tangent line. All right, the rule that we're actually going to look at, though, involves us using the corresponding point on the inverse. So the relationship we're going to look at will relate the tangent line I just drew over here to the tangent line of this corresponding point. So two things you'll notice. One is that one line is a lot steeper than the other. The other is that they are both going the same direction, meaning both slopes are positive. So let's look at numerically what they are. For the original function, we can find the slope of the tangent line by finding the derivative, y prime. Derivative of x squared minus 4 is just 2x. And if I want the slope of this particular tangent line, we're going to use x equal to 1. So that has a slope of 2. Now with the inverse function, we know that it's defined as the square root of x plus 4. All right, but remember when we take derivatives, we want roots to be written as powers. So when I go to find the derivative of y inverse, we can use the chain rule. Right, bring the 1/2 down, keep the inside the same, subtract 1 from the power, and then multiply by the derivative of the inside. So writing this in a more plug a number in friendly kind of way, I'm going to move that negative 1/2 exponent down to the bottom. And I'm going to write it as a root again. And there we go. That's our derivative. So if I want the slope of this tangent line, notice the x-coordinate on the inverse function is -3, right? That was the y-coordinate on the original. So to find the slope of the tangent line that I drew, I need to know y inverse prime of -3. And when I substitute that into the derivative I just found, we end up getting 1/2. So there is a relationship here. For the original function, the slope of the tangent line was 2. For the inverse function, the slope of the tangent line was 1/2. That was the reciprocal of the tangent line on the original function. And the thing is, no matter which value of x I choose, this is going to end up working out for any value. So like, for example, if I drew a tangent line at 2, or attempt to, that would have a slope of 4. The corresponding point would have a tangent line that looks like this, which has a slope of 1/4, the reciprocal of 4. So that's to say the rule that we're going to use to find derivatives of inverses is, let's say that we have any function f evaluated at some x value that we'll call c. Let's say that the y-coordinate at that point is some number. F inverse prime at number, because remember the input for inverse was the output of the original, is the reciprocal of f prime at the x value. So a couple things to note here. Inputs are switched, value is reciprocaled, switched and flipped. And this is a powerful rule because it actually enables us to find derivatives of inverse functions without actually needing to solve for the inverse. So in the example we just did, I went through the algebra and I showed you how this worked out. You don't have to do that because of this rule. So let's look at some examples. First example, let's say we have f of x equal to x cubed plus 5x minus 1. It would be kind of horrible to try to go and find the inverse of that. So instead, we can use the rule to figure out f inverse prime of -7. And let's say we're also given that f of -1 is -7. So to work this one again, I do not need to find f inverse. All I actually need is f prime. And I can get f prime just by using my power rule. Now if I plug in -1 to the derivative of f, okay, this is going to work out to 8. That's f prime of 1. If I want to know the derivative of the inverse at the corresponding point, I just need to flip that, as in flip the fraction. So f inverse prime of -7 would just be 1/8. Easy. See, we didn't have to go through any kind of rough algebra to solve for an inverse. We just used the reciprocal relationship of the tangent line of a function and the tangent line of the inverse at the corresponding point. Let's do another example. Okay, so we have a function, a rational function, and we have a domain restriction. Again, the point of this guy is just to make sure that f of x is 1-to-1, so that f inverse is a function. So here we're given that f of 1 is 3. We can verify that that's true by substituting 1 into f of x. And we want to know the derivative of f inverse at 3. So again, I don't need f inverse. All I need to do is take the derivative of f. For this one, we're going to need to use our quotient rule. So remember how that one works. You got derivative of the top times the bottom minus the top times derivative of the bottom over the bottom squared. Derivative of the top is 1. Bottom we got x plus 1 minus top, or bottom we have x plus 1. Oh, whoops, that's 5. Times the derivative of the bottom is 1. And then oh, wait, hold on. Early morning. Okay. So derivative of the top is 1. The bottom is x plus 1. Top we have x plus 5. Derivative of the bottom is 1. And this is all over the bottom squared. So if I do a little bit of distributing and rearranging, and if you need to, you can pause the video and see that you come up with the same thing. You end up with -4 over x plus 1 squared. So now that we have f prime, we can plug 1, that's the x from the original statement, into f prime. A little bit of arithmetic will tell you that this is equal to -1, which is not our answer, so I shouldn't circle it. All right, so that's the derivative of f. We want the derivative of f inverse at the corresponding point. So all I need to do is take the reciprocal of that. So 1 over that. And coincidentally, not the norm, coincidentally, this works out to also be -1. All right, one more example. Let's do something with a little bit of trig. Okay. So again, we've got a trig function. This time we actually have a domain restriction. And again, the only purpose of that is to make sure that f is 1 to 1, meaning f inverse is a function and passes the vertical line test. So again, I don't need to worry about finding the inverse of that. I mean, the inverse would just be arc sine of 4x, but that's for the next video. We just need to know what f prime is. So f prime, we're going to get by using our chain rule. Okay, and we get 4 cosine of 4x. So then if I substitute the original x value, pi over 16, to derivative of f, all right, we'll get 4 times cosine of 4 times pi over 16, which would be pi over 4. We know cosine of pi over 4 is the square root of 2 over 2. And when I multiply by 4, I get 2 square root 2. So this is the derivative of f at that point. If I want to know the derivative of f inverse at the corresponding point, then I need to take the reciprocal of this. So f inverse prime at the corresponding point is 1 over 2 square root 2. And if you really want to, you could rationalize the denominator and get square root of 2 over 4, but that doesn't really matter. So in summary, if I want to find the derivative of an inverse function, I don't need to find the inverse function. I don't need to solve for f inverse. All I need to do is take the derivative of f, find f prime at the original x value, and then take the reciprocal of the result. So 1 over the result. And that's basically it. But it is important for you, especially going into the next video, to kind of just remember what inverses are. Remember, every function has an input and an output. With an inverse, the input and output are flipped. So if I have a function f, right, whatever I get out from f is what I would put into f inverse. And whatever I put into f is what I would get out of f inverse. I'll definitely go into more detail with that in the next video. But yeah, here you go. Simple examples. Have fun.